Hello and welcome to my talk with an obnoxiously long name, which I think is fully descriptive as to what it is. So that we are going to be applying wisdom of the crowds to generate a dynamic routing strategy for repair technicians performing tasks of stochastic duration in taxicab geometry. So, why do we care about this? In the real world, there are many examples of technicians that need to do segments of jobs, like they need to have routes created, and the true length or nature of these jobs can only be approximated, while the task itself might be of variable length, like there might be some randomness to it. The actual nature of the job very often isn't fully known until someone with technical expertise gets to a job. In the past, I have some experience with the cable industry, and there are all sorts of problems with residential, commercial, and maintenance techs, sorts of problems that they could run into that unless someone of their experience observed the problem, correctly categorizing the nature of the problem wasn't necessarily possible. Very often, techs would get to a location, they would have a job that they found to be very different from the original task, and the job length would suddenly be much larger than anticipated, which all of the jobs are already pre-routed on these techs, and they all run with the maximum possible jobs. So even if other techs finish their jobs sooner, there was a need to correctly route them in such a way to account for these jobs that like went over in length, and sometimes they went under in length. So this is an example of a mathematical game where there is a lot of unknown information. So we can't go ahead and look at the end result of running some sort of simulation and then make decisions upon that. We have to, while the simulation is running, have the strategy, make decisions, and then use that strategy, because otherwise, we presume that any sort of strategy that makes decisions after the fact is aware of the outcome of events which are truly random, or at least that the randomness is not observable to any sort of process that could make decisions during the fact. All right. So uh, Speaking of randomness, first we should probably talk about true random and pseudo-randomness. So true random pretty much comes out of physical phenomenon. Like you have nuclear decay, you could use the least significant bit from the shadows in a room, from images that you took, or the weather. But for actual random things, it's going to be something that is a physical phenomenon. And the most common reason that we would want to use something that is true random is pretty much cryptography, or some sort of uh, like application where it would be very bad if the random thing that we used was ever determined. So very often, true random is used to generate cryptographic keys, which if you get the information used to generate the keys, you can generate the keys, which makes them no longer secure. So you want any sort of cryptographic applications to use something that cannot be predicted, and true random things ideally cannot be predicted. And then we run into pseudo-randomness. Pseudo-randomness is going to be generated by algorithms or math. Strictly speaking, computers are deterministic, or at least hopefully are deterministic. And if like they generate random numbers without any sort of access to some sort of physical phenomena, they cannot generate truly random things. But these pseudo random numbers can be really useful for simulations because we might want to compare one simulation to another one. And if we have truly random numbers in both simulations, while the probability that those simulations are incorrectly ranked due to the lack of like reproducibility, that randomness A and randomness B are fundamentally different, is kind of low. That problem still exists, and especially when we're comparing very complex situations, we want to lower the number of possible variables that could allow us to go to an erroneous conclusion. We want to minimize those. So very much in simulation-based applications, we want to go with things that are pseudo-random. So when we're talking about pseudo-randomness, while it is strictly speaking something that is reproducible and technically predictable in the strictest sense, there are still attributes about being random that these things need to meet, or they're not going to be useful for many applications that we'd want to use statistically random things for. So to that end, there exist a number of tests. The die-hard tests are probably the most common ones, and I have a list of common die-hard tests here that test different attributes of randomness for the quality of the randomness. So, despite pseudo-randomness being predictable randomness, it still has these qualities that we call randomness that we need to have. So, um, a good source of reproducible randomness is the XOR pseudo-random number generator, which there's a particular paper that I borrowed this technique of creating an XOR pseudo-random number generator where there are a few constants used, and because of various properties of these constants, we are able to create statistically random numbers, or at least statistically pseudo-random numbers. So we've got a randomness, but we don't want it to be, say, a task that is a uniform distribution. That probably wouldn't be that accurate. Most tasks aren't uniformly distributed. Uh, some might be like normally distributed, but there are many different distributions that are used for determining how long a task should take. This particular distribution is fairly common for task length and is fairly easy to calculate, or at least mostly easy to calculate in the grand scheme of things, since there are many distributions whose method of like their cumulative distribution function is not easily calculated. And here I have an example of this Weibull distribution function, the cumulative distribution function, in terms of probability and time, and a graph of those two things so we can get a sense of it. And typically for this one, so long we have the inputs L and K, and so long as L is 1, typically K like tends to be the mean of this. When there's differing L values, the mean becomes like a very irrational number. So with this example, uh, like about half of the probability is like already like under the curve for like 1. So um, like this like it is a pretty good distribution for task, and most tasks aren't just like very like you could equally spend an infinite amount of time or zero amount of time. There tends to be a gradient of like the the possibility of this task being extremely easy is fairly low, then the mean, it tends to be fairly common, and then as the task might spiral into some sort of complex problem, the probability of that lowers and lowers. So this distribution does a pretty good job of modeling that. All right. So this is just an example with different values of L and K, which are just parameters of this distribution for both in terms of time and in terms of probability. So we have a bit of a problem with the mean of this distribution, and the variance for that matter, requires the gamma function, which, like, calculating it for integers, actually kind of easy because it's just a factorial function. But for positive reals, which if we go ahead and examine that function again, only under certain cases are we going to be able to deal with things that aren't fractional or irrational numbers. Oh, they actually, yeah, they you could still get some irrational numbers there, but like most of the time that we're calculating the mean, we're going to have to use the gamma function in relation to positive real numbers. So we have this not so friendly equation, and if we were just limited to like, oh, we're just calculating gamma for integers, well, that's like typically like an intro to programming class exercise, implementing factorial, which is also a good example of recursion, or we could do the iterative version. So like that function is fairly easy to implement, but we don't have that option. We've got to like somehow calculate this value. So another option that we could use is Monte Carlo method, which is one of my favorite methods for calculating most things. Of we can attempt to use randomness to query a search space and try and determine answers with randomness. So we just go ahead and run this distribution with a random selection, and then we go ahead and average that selection, and the value of that selection is going to go ahead and approach the real value the more that we do this. But mathematically, we need to do this an infinite number of times. So if we go ahead and examine like doing that, we go ahead and do a quick like Monte Carlo test. You can see that at 256, we are very close to the actual number. So in this case, we could use Monte Carlo without too much of a computational hit. And if we go ahead and calculate that, that's 5 milliseconds, um, which uh, could add up depending upon how we're using the distribution, or if we're having to recalculate distributions. In this particular implementation, the distribution goes ahead and calculates the mean in the constructor. But if we were if whatever we were doing simulation wise required a very large number of statistical distributions of different values, then that 5 milliseconds would quickly add up, as opposed to an amount of milliseconds that unfortunately can't be measured because of how fast it went. So, uh, in order to avoid doing this approximation, which has at least a minimal computational cost, Paul Gottfried went ahead and created an implementation of the gamma function, which is very computationally fast. As you can see, it still takes an amount of time. It's just unable to be measured on this machine, which if I ran it enough times and just divided it by the number of times it ran, we could get some sort of non-zero measurement. Because yeah, this doesn't run in like constant zero time. That would be a talk unto itself if anything ran in constant zero time on a computer. But anyways, so, like, there we go. That we've got our randomness, we've got our distribution, and a way of calculating the mean of our distribution. So let's talk about taxicab or Manhattan distance. So this is very much used whenever you're having to deal with like city streets, like Google. Uh, like Maps tends to use this in a lot of environments because when you're dealing with urban areas, most of the time the streets are laid out in a grid, and the Euclidean distance between A and B would not be possible because there's buildings in the way. You have to follow the roads, which go ahead and make the shortest distance between any 2 points the distance between ax and the distance between by added together. So this is something that a lot of people aren't very familiar with, but in a lot of situations, this means of measuring distance more accurately represents a particular environment. So that's one of the reasons that this simulation is going to be done using Manhattan or taxicab distance. All right. So, elements of the simulation. So, we've got jobs, which have positions, which are represented by taxicab positions. They have difficulties, which are represented by statistical distributions, in particular, the Weibull distribution that we went ahead and made. Jobs also count the number of days they are not completed. They have a unique ID for their title. And repair techs. So repair techs uh, like have the attributes of like they have a unique title, they have a position, they have a next job, they have a list of completed jobs, and they can be made busy once they start working on a job until they complete that job. And then they also have a speed. So techs, like when they're given a job, will go ahead and like when the simulation runs a turn, they will then move towards that job an amount equal to their speed. If they are ever at the start of a turn at a job, they will go ahead and start working at that job, and they will be made busy an amount of time calculated by the uh, distribution that is the difficulty of that job. If a tech is busy, at the start of a turn, their busy counter will be decremented. If their busy counter is ever decremented to 0 or below, they are no longer busy and they can receive another job and go ahead and drive towards that job and ideally complete another job. So, um, in order to examine various strategies, we are looking at the attributes of distance of a job, the mean difficulty of a job, the days not completed of a job, and then there's going to be the wisdom of the crowd, which is going to try and combine those three metrics. So for these three, they're going to try and get the minimum distance, the minimum difficulty, and the minimum days out. This greedy first that everything inherits from, like it goes ahead and just uses a like its method of determining what is smallest is just whatever this first in the job pool, like at the start of the array, which effectively, since the array is randomly generated, goes ahead and makes greedy first. Completely random assignment of jobs, which is a good sort of control for comparing these other sorts of strategy. And then wisdom of the crowd, since all of this, like we can't determine how long a job will be like after the fact, because like all of that is like determined. We have to make decisions like in the moment, so we can't like go ahead and run these three and then after the fact combine them. We have to combine them during the routing process. So we go ahead and use weights with these three different signals of distance, difficulty, and days not completed to make decisions as to which job should be routed next. So if we go ahead and look at greedy first, well, this is an example of a simulation where the throughput of the things trying to process stuff in the simulation uh, cannot keep up with what's being produced. Like at the start of each day, there are too many jobs being produced, and the days not completed goes ahead and just like spirals out of control. The remaining difficulty, so this is the number of jobs left over, completely out of control. And we can see that total travel, this remains pretty consistent. Same thing for completed difficulty. But we aren't completing enough jobs to keep up with the amount of jobs that are produced every day. And if we go ahead and look at a graphical representation between day 1, 10, and 20, day 1, we can see that the paths aren't great because they are literally random. But by the time we get to day 10, we have far too many jobs and 20, it's just spiraling more and more out of control. So randomly assigning jobs will not get enough jobs done in order to like ever like keep the number of jobs low or to a finite number. This simulation will just like diverge towards infinity. So ideally, we don't want to do that with our routing strategy. So we're going to go ahead and look at greedy distance. Well, greedy distance, we go ahead and look at remaining difficulty. We can see that this is, while fluctuating, not diverging towards positive infinity. So that is definitely something good. The day is not completed. Like we are staying like pretty consistent with not diverging towards infinity, and like going just assigning texts based upon what's closest to them appears to be a pretty good strategy. And if we go ahead and look at the graphical map, day 1 we have some leftover jobs here. Day 10 we still have leftover jobs, but this hasn't spiraled out of control. And still day 20, while we have leftover jobs, eventually if we look at that graph, that the remaining difficulty, while it does spike at times, it goes back down at times as well. So while there's an amount of flux to this, the throughput is such that we aren't diverging towards infinity. So this is a viable solution for not having an infinite number of jobs to complete. So if we go ahead and look at difficulty, well, that doesn't seem to work. If we look at the remaining difficulty, that diverges towards infinity. And if we look at the map, yep, that is not an effective strategy. And we can see that the distance these techs are driving to get to their jobs is very far and not very efficient. And we can see something similar for days not completed, that this like it diverges towards infinity. And so too on this one, the routes are not very well designed, and they are like the number of jobs to do are diverging towards infinity, which is not what we want. So you might think, okay, uh, days not completed in difficulty, those aren't worthwhile metrics, but they might be. So we're going to go ahead and test out this wisdom of the crowds, which is going to go ahead and take a weighted measure of distance, difficulty, and days not completed, and calculate a metric based upon that and find the shortest of that particular metric. So if we go ahead and in this case, like we need to determine the weights, so we're going to go ahead and test all weights, all combinations of 0.5, 1, and 2 for these three attributes. So that goes ahead and gets us this table, which if we go ahead and look at our total traveled, remaining difficulty, completed difficulty, and days not completed, that while greedy distance is pretty good compared to these individual attributes, if we go ahead and look at some of the wisdom of the crowds with various weights, we can find that it sometimes produces solutions which are more efficient than just purely looking at distance. And we are going to be looking at a weights of let me see, zero point 0.5, zero point 0.5, and 0.5, 0.51, and 0.5, 2, 1, and 0.5. So like these two are generally like the point 0.5, point 0.5, point 0.5, and the 0.51 and point 0.5 are good at lowering the amount of like travel. Well, like one of them's really good at travel, but both of these two are very good at completing jobs. Actually, all three of these are better at completing jobs, but this last one is very good at making sure days not completed is low. Like when we have maintenance duties to attend to, we want to make sure that equipment does not stay in disrepair for an extended amount of time, which these sets of weights, if we were more interested in that metric, we would go ahead and choose these sets of weights for routing our text. So if we look at this table down here, we can see at completed difficulty, like this one, like greedy averages at 48.78, and all three of these are better, with the best one being at 49.84, which remaining difficulty and completed difficulty, these two are extremely related and could be argued to be the same sort of information, just like viewed from different lenses. So it makes sense that the one that is best at completing things is the best at leaving as few jobs as possible. Um, and we can see that it does, like if we were favoring like we need to complete as many jobs, well, we are traveling slightly more. But if we go ahead and look at like point 0.5, point 0.5, and point 0.5, distance traveled is lower than the one that only cares about distance. And its completed is still higher, though this one for days not completed is very bad. So if we cared most about days not completed, we would choose these weights. So we can go ahead and like look at these calculated and simulated over 50 days. And we can go ahead and do the same for difficulty, that now this is total traveled, so on this one, point 0.5, yeah, that one is blue. So most of the time, blue is the lowest line on this one. For this one, since this is difficulty, we want the line to be high on difficulty, and red, actually, yeah, red is the one that has the highest average, which this one has a decent amount of variance to it uh, for that. Oh, this is remaining difficulty, my bad, which we want the lowest on that, so that's why red is on average lower most of the time. Completed difficulty, this one you can see the red line is higher most of the time, and days not completed. So this one, greedy distance, is better than the first two wisdom of the crowd weights, but the last one, the gold line, is significantly better and has far lower variance. And you can see for greedy and two of the wisdom approaches with different weights, that there is something that happens in probably like something to do with the entropy here, that is reflected in this, that the gold line is somehow able to avoid, and it would probably take some amount of diving to fully understand what is generating this trend of increase while it is not being increased there. So, closing thoughts. Like, there could be other forms of data that are useful for jobs, for trying to get ideal number of jobs completed, lowering the amount of travel, and making sure that jobs are completed within a timely manner and equipment isn't in disrepair. But we should also like make sure that the text like that's at some point we're actually considering the satisfaction of these texts, because there are some configurations where we might be creating optimal routes, but those routes are either difficult to execute or are in some way psychologically disfavorable for our technicians, and that could be some sort of hit. Well, other than ideally we care about our workers, which might be a foreign idea in the U.S., like that sort of negative impact upon their happiness will probably reflect in lower performance. So that is probably some sort of hidden attribute that we could increase efficiency by just making people happier, and probably also increasing the amount of retention that we have with our techs. And another thing to consider is that as the day goes on in these simulations, the weights that we have at the start of the day might not be optimal at the middle part of the day or the end of the day. So this leaves us with a lot of possible weights, which also could change with time. So these are a lot of possibilities. So attempting to find the optimal combination, like it might not be possible to brute force that, which determining the ideal weights, it might be suitable to use a genetic approach in order to try and find these ideal values. Like with further research, that would probably be a good area of research to try and find the weights and the changes to those weights which result in optimal outcomes. All right. Well, I hope everyone learned something, and I hope everyone has a good day.